Our last shuffle for today is shuffle number 40. It is a judicious Klondike in which the stacking is similar to the previous shuffle, shuffle 39, except for the fact that the left pile at the very end is stacked on top of the right pile. Okay, so let's go ahead and demonstrate this shuffle and obtain the permutation representation for it. So we begin with our ordered packet 1 through 8, and we perform the shuffle. So the judicious Klondike shuffle is always the same in terms of the first set of actions. We take the top and bottom cards off as 1 and set them down into the first pile. We take the top and bottom card off as 1 and set those down into a second pile. Top and bottom cards off as 1 into a third. The last 2 cards make up the fourth pile. Stacking is as follows. Pile 4 on top of pile 2, pile 3 on top of pile 1, and then we will stack the left pile on top of the right. So recall, this is pile 1, 2, 3, 4. So pile 4 is right here, and it leaps over its neighbor and gets set on top of pile 2. Pile 3 leaps over its neighbor and gets set on top of pile 1. And then we stack the left pile on top of the right. And so let's see what is the new ordering of the cards, and will that enable us to write Cauchy's 2-line notation for this permutation. So in Cauchy's 2-line notation, we obtain the following. So the top row is always 1 through 8, and then we get 3, 6, 1, 8, 4, 5, 2, 7. Converting this to cycle notation, we obtain the following. 1 goes to 3, so there's an arrow from 1 to 3, and then 3 returns back to 1, so it cycles back to 1. So this is called a 2-cycle, also a transposition. That's another name for it. Next, we get a monster cycle, a 6-cycle. So 2 goes to 6, so we have an arrow from 2 to 6. 6 goes to 5, so there we go, an arrow from 6 to 5. 5 goes to 4, so we have an arrow from 5 to 4. 4 goes to 8, so we have an arrow from 4 to 8. 8 goes to 7, so we have an arrow from 8 to 7. And then 7 returns back to 2, so that completes that cycle, which is actually a 6-cycle. So if we color code our values, we obtain the following representation. And let me just remind you of the color coding convention for Bessey Sequences. So the position values 1, 4, 6, 7 are color coded black. The position values 2, 3, 5, 8 are color coded red. And this will help us determine the effect of the shuffle on our Bessey sequence structure. So we can see here that black 1 goes to red 3, which wraps around to black 1. Red 2 goes to black 6, which goes to red 5, which goes to black 4, which goes to red 8, which goes to black 7, which wraps around to red 2. So we see that each value gets sent to a value of the opposite color. And when this happens, inversion has occurred. So what this means then is that the cards that originally began in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment, and vice versa. The cards that originally began in positions 2, 3, 5, 8 get moved to positions 1, 4, 6, 7. In fact, we can see how they've gotten moved taking a look at our cycle notation for the permutation. So every single card is moving location, but it's doing it in such a way that there's a wholesale replacement between the positions 1, 4, 6, 7 and the position 2, 3, 5, 8. Now it will be very helpful to see this effect on our Bessey sequence 1001, 0110, because this shuffle apparently should invert this sequence. So let's go ahead and perform the shuffle. So this is the judicious Klondike. So you take the top and bottom off as 1, set that down as pile 1. top and bottom down is 1, pile 2, top and bottom off is 1, pile 3. The last 2 become pile 4. Now we're stacking the 4th pile on top of the 2nd, the 3rd pile on top of the 1st, and then we're stacking the left pile on top of the right. So we should now get the inversion. So we should get a 0, 1, 1, 0, 1, 0, 0, 1. So our original Bessey sequence has been inverted. And so the zeros and ones have switched places according to the assignments described here in our cycle notation of this permutation. So taking a look at our shuffle diagram for shuffle number 40, we see the following. Since we have a transposition 1, 3, we should expect to see a double arrow between 1 and 3, which we do. Also, this 6th cycle is as follows. 2 goes to 6, which goes to 5, which goes to 4, which goes to 8, which goes to 7, which wraps around to 2. So let's go ahead and begin at 2. So there will be an arrow from 2 down to 6, which there is, an arrow from 6 down to 5, which there is, an arrow from 5 to 4, right there, and then an arrow from 4 up to 8, and then an arrow from 8 to 7, and then an arrow from 7 back to 2, completing that 6th cycle. So in particular, this shuffle is of order 6, since we have a transposition here and a 6th cycle. So it would require performing this shuffle 6 times to return a packet of 8 cards back to its original order. Okay, so finally, let's show an application of all of this today.